This research paper presents a groundbreaking approach to group activity recognition, GAR, through the use of a spatial-temporal panoramic graph. This innovative method addresses the limitations of existing RGB-based methods, which are often hindered by challenges such as background variations, occlusions, and motion blurs, and are computationally expensive. The proposed method leverages multi-person skeletons and objects to encapsulate group activity, eliminating the need for accurate individual annotations and specialized interaction reasoning modules. It involves extracting skeleton coordinates using pose estimation and tracking algorithms, followed by the application of Multi-person Panoramic GCN, MP-GCN, to predict group activities. The authors design a panoramic graph that incorporates skeleton coordinates and objects, enabling the application of Graph Convolutional Networks, GCNs, to model intra-person, inter-person, and person-object interactions through spatial-temporal graph convolutions. This approach offers a lightweight and informative representation of human motions. Extensive experiments on volleyball and NBA datasets demonstrate the state-of-the-art performance of MP-GCN in both accuracy and efficiency, outperforming RGB-based approaches using only estimated 2D keypoints as input. GAR is a crucial task in video understanding, with applications in surveillance, social scene understanding, and sports analysis. The proposed spatial-temporal panoramic graph approach provides an effective alternative to RGB video, enabling the unification of intra-person, inter-person, and person-object interactive modeling through spatial-temporal graph convolutions. Traditional RGB-based methods for group activity recognition are hindered by high computational and memory demands due to large data sizes. To overcome these limitations, leveraging human pose estimation offers a promising alternative. By extracting keypoints from pose estimation backbones, researchers can tap into the rich structural information inherent in human skeletons. However, current methods struggle to effectively model the complex relationships between keypoints, relying on relational reasoning or hierarchical models that add complexity. The authors propose a novel approach, applying graph convolutional networks, GCNs, to skeletal graphs, which naturally provide a strong prior for spatial and temporal convolutions. This framework has demonstrated significant success in single-person skeletal action recognition, but its adaptation to multi-person scenarios remains a crucial challenge. By addressing this gap, the authors aim to develop a more efficient and effective method for group activity recognition, capitalizing on the structural priors inherent in human pose. The proposed methodology leverages the strengths of GCNs in modeling complex graph structures, enabling the capture of subtle spatial and temporal patterns in human skeletons. By doing so, the authors pave the way for more accurate and efficient group activity recognition, with far-reaching implications for applications such as surveillance, healthcare, and human-computer interaction. The novel pipeline for skeleton-based group activity recognition, GAR, addresses the limitations of previous methods by introducing a unique approach. It starts with estimating human poses from videos and constructing a multi-person skeleton graph. The recognition process utilizes a spatial-temporal graph convolution network, differing from conventional methods that rely on ground truth tracklets. Instead, this pipeline employs a reassignment strategy and pose tracking algorithms for consistent identity assignments. Additionally, a panoramic multi-person object graph is designed, integrating keypoints of multiple human skeletons and objects to overcome the constraints of single-person graph scales and the lack of object information. Experimental evaluations on volleyball, NBA, and kinetics demonstrate that the proposed method outperforms state-of-the-art keypoint-based methods, with significantly lower computation costs compared to RGB-based methods. In group activity recognition, GAR, interaction modeling is crucial for accurately depicting relationships between actors. Interaction graphs provide a visual representation of these relationships, facilitating the extraction of features and learning of interactions. However, in skeleton-based GAR, computational requirements and background variations necessitate efficient methods. Graph Convolutional Networks, GCNs, have been applied to skeleton sequences, particularly in multi-person scenarios, to model interactive relations for recognition. Conventional GCN methods, however, have limitations in capturing complex interactions. They often fail to consider interbody and intrabody joint relationships, which are essential for accurate group activity recognition. To address these limitations, a novel approach constructs a multi-person graph that incorporates both interbody and intrabody joint relationships. This graph focuses on introducing key point information in group activities, enabling the modeling of complex interactions between individuals. By leveraging this approach, GAR systems can better recognize and interpret group activities, despite variations in background and computational constraints. The authors introduce a multi-person object graph, referred to as a panoramic graph, to address the limitations of traditional video and skeleton representations in group activity sequence analysis. This graph provides a comprehensive view of all individuals and objects involved in the scene. The human skeleton representation is formulated as a spatial graph, G, comprising a vertex set, V, of end joints and an edge set, E, representing bone connections between joints. The relational adjacency matrix, A, denotes all edges, with element Aij representing the strength of edge Eij. The feature map, X, is a C-channel representation of the sequence in T frames, typically consisting of 2D, 3D joint coordinates. The authors review the Graph Convolutional Network, GCN, paradigm, which typically consists of basic blocks composed of spatial graph convolution, SGC, and temporal convolution network, TCN, layers. These layers capture spatial relationships among skeleton joints within a single frame and temporal dependencies across multiple frames, respectively. The SGC operation is defined as equation 1, where fin and fout are input and output features of corresponding joints, respectively, and Z, Vj, serves as a normalizing term to balance the influence of different subsets. To address the limitation of traditional skeleton representations, which often lack object information, the authors introduce a human object graph. This graph represents an activity sequence as X, where M is the number of participants, and N is the total number of joints and object keypoints. The authors propose integrating object keypoints with human pose, expanding the skeletal sequence to include object information. In this paper, the ball is represented as a single point corresponding to the center of its bounding box and is connected to both hands. The authors propose a novel architecture, MP-GCN, for multi-person pose estimation and tracking. This architecture consists of a pose backbone, object backbone, and tracker, interconnected through convolutional and graph convolutional layers. The pose backbone employs multi-scaled temporal convolution to extract spatial and temporal features from input data. The object backbone uses a similar architecture to extract features from object keypoints. A tracker module is responsible for reassigning joints and bones to their corresponding individuals. A multi-person graph is introduced, viewing all individuals in a scene as a unified group. This graph is represented by an adjacency matrix, where diagonal blocks capture intrabody connections and off-diagonal blocks represent interbody relationships. The graph is constructed by defining the natural body topology as the intrabody graph and introducing pairwise interbody links. The authors then create a panoramic multi-person object graph by integrating human object and multi-person graphs. Spatial graph convolution is applied to extract information embedded in the multi-person object skeleton graph. This graph convolution operation is defined as a matrix production, elementwise production, and concatenation of input features and the adjacency matrix. A basic block consisting of graph convolution, batch normalization, and ReLU activation is used to extract features from the graph. This block is repeated multiple times to extract features at different scales. Group activity recognition, GAR, involves identifying the actions of individuals within a group. To tackle this challenge, researchers propose a novel method utilizing a multi-person spatial graph convolutional network, MP-GCN. This approach represents spatial relationships between individuals in a group activity through a panoramic graph, implemented with an adjacency matrix that captures both intraperson and interperson connections. The MP-GCN architecture consists of 4 input branches and a main branch. Each input branch extracts low-level features from skeletal data, including joint, bone, joint motion, and bone motion aspects. These feature maps are concatenated into the main branch at an early stage, followed by additional basic blocks and a classification head. The basic block comprises three key components: a spatial graph convolution, SGC, a multi-scale temporal convolutional network, TCN, and a spatial-temporal person attention block with module-wise residual links. The SGC performs graph convolution on the entire panoramic graph, maintaining the graph scale throughout the network. The TCN captures temporal dynamics in consecutive frames using a 4-branch multi-scale temporal convolution layer. Each branch consists of a bottleneck layer, batch norm, ReLU, and 3x1 convolutional layers with specified dilation or a max pooling layer. The spatial-temporal person attention module computes attention scores for M people across T frames, averaging feature maps in person and frame dimensions, and applying a multi-head attention mechanism to capture key individuals throughout an activity. This novel MP-GCN model leverages spatial relationships between individuals in a group activity, capturing both intraperson and interperson interactions through a singular graph convolution framework. This approach offers a more efficient and effective solution for GAR compared to conventional ensemble solutions. The authors propose a novel attention module in the MP-GCN framework, which concatenates averaged features into a vector and applies 2 convolutional layers to derive person-wise and frame-wise scores. These scores are multiplied to generate a final spatial temporal attention map, enabling the model to focus on key individuals and objects in crowded scenes and mitigate the impact of irrelevant roles. To address the lack of publicly available datasets, the authors extract 2D skeleton coordinates from original RGB videos using pre-trained pose estimators and object detectors. They leverage a read tracker to assign unique IDs to the same person identified across frames, acknowledging that occlusions, misdetections, and the identification of non-relevant individuals can occur frequently. To enhance data consistency and filter out irrelevant individuals, the authors develop a pose assignment strategy that maps a variable number of individuals per frame to a fixed number m. This strategy involves evaluating the activeness of each person using a confidence score and a detection confidence score. The confidence score is calculated using the standard deviation of the trajectory of each person's center coordinates. The pose reassignment strategy consists of 2 stages. First, it selects individuals with the highest m scores, where the score is determined by the confidence score and the activeness score. The chosen track IDs are then mapped to a fixed range using a modulo operation. In case of conflicts, the person with a smaller track ID is assigned, while others are reserved for the second assignment. The remaining individuals are allocated to available indices in order, prioritizing those who are more likely to play a significant role in group activities and enhancing temporal consistency of the obtained skeletal data. The authors present their experimental setup and implementation details for the proposed skeleton-based group activity recognition model. They utilize 2 datasets: Volleyball dataset and NBA dataset. The Volleyball dataset contains 4,830 clips from 55 volleyball game records, labeled with 1 of 8 group activities, individual actions, and bounding boxes for every athlete. For fully supervised studies, researchers use group activities, individual action labels, and ground truth person bounding boxes of the middle 20 frames. The authors report multi-class classification accuracy, MCA, for group activity and mean classification accuracy of individual action, IMCA, on volleyball fully supervised. For weakly supervised methods, only group-level activity labels are utilized, and they report MCA and merged MCA, MMCA, on volleyball weakly supervised. The NBA dataset includes 9,172 clips derived from 181 NBA game records, labeled with 1 of 9 basketball scoring activities. It is the largest dataset currently for group activity recognition, providing only group-level activity annotations. For evaluation, the authors report multi-class accuracy, MCA, and mean per-class accuracy, MP-CA, consistent with previous methods. The authors adopt YOLOV 8 for pose estimation and object detection, fine-tuning the pre-trained model on a custom dataset for detecting basketballs and basketball nets on the NBA dataset. They set the number of actors in each frame to 12 and the number of frames to the original length of each clip. The training and testing batch size is set to 16, training the model for 65 epochs with a warm-up strategy for the first 5 epochs. The learning rate is initially set to 0.1 and decays according to a cosine scheduler after the 5th epoch. Cross-entropy loss is used as the training objective, and an SGD optimizer with Nesterov momentum of 0.9 and weight decay of 0.0002 is employed. In the context of group activity recognition, the multi-person Graph Convolutional Network (MP-GCN) model outperforms state-of-the-art methods on the volleyball dataset. It achieves a remarkable 95.5% in multiclass activity (MCA) and 84.6% in individual multiclass activity (IMCA) in fully supervised settings. The MP-GCN model utilizing YOLOV8X for object detection also shows effectiveness in weakly supervised settings, with 92.8% in MCA and 96.1% in IMCA. This demonstrates the model's ability to predict group activity from complex scenes and its complementarity with RGB-based methods. The MP-GCN model combines the benefits of keypoint-based and RGB-based methods, leveraging both the spatial and temporal relationships between individuals within a group. This is achieved through the use of a graph convolutional network that processes skeletal data extracted by Composer, which employs HRNet with ground truth human bounding boxes. The results highlight the potential of the MP-GCN model for real-world applications requiring accurate group activity recognition, such as sports analytics, surveillance, and human-computer interaction. The authors present a skeleton-based graph attention network for action recognition, comparing their method to state-of-the-art approaches on the NBA dataset. Their method, MP-GCN, outperforms other methods in terms of MCA and MPCA, with significantly fewer parameters and lower computational costs. Specifically, MP-GCN with LaTeFusion achieves an MCA of 78.7 and MPCA of 74.6, surpassing video-based methods. In the weakly supervised setting, the authors replace ground truth bounding boxes with estimated tracklets obtained using YOLOV8, demonstrating their method's compatibility with both high-quality and noisy keypoints data. The results show that their method can still achieve satisfying results, with an MCA of 92.8% and MMCA of 96.1%. The authors also provide an ablation study on the graph structure, experimenting with different settings on the volleyball dataset, comparing the proposed multi-person graph to 2 baseline settings. They report the number of parameters and flops for each method, highlighting the computational efficiency of their approach. The authors present a comprehensive comparison of various graph structures, evaluating their performance on the volleyball fully supervised dataset. Table 3 displays the results, showcasing the effectiveness of the panoramic graph structure, which achieves a 1.5% improvement in MCA over the baseline model, with a moderate increase in parameters and flops. Notably, the panoramic graph with both intra- and interperson connections outperforms the baseline model with non-shared weights. The authors also conduct an ablation study on the NBA dataset, examining the impact of the number of people, M, on the M in MCA metric. As presented in Table 4, the results demonstrate that M equals 12 achieves the highest accuracy, consistent with the typical composition of a basketball game. Furthermore, the authors investigate the effect of object information on the graph structure, exploring various configurations. Table 5 presents the results, showing that incorporating object keypoints, such as the ball and basketball net, enhances recognition accuracy. Specifically, the pose M plus ball plus net graph structure, which includes M people and V object points connected to the hands of each actor, achieves higher accuracy compared to separating object keypoints from the multi-person skeletons. The results highlight the effectiveness and generalizability of the proposed panoramic graph, which successfully integrates object information and maintains key roles on the court. The findings suggest that the reassignment strategy effectively captures the relationships between people and objects, leading to improved accuracy in action recognition tasks. The authors of the research paper visualize their proposed skeleton-based graph attention refinement (GAR) method via a panoramic graph, showcasing its effectiveness in extracting human skeletons, object keypoints, and activation maps. In Figure 3, they illustrate the original pose estimation results, skeletal data after pose reassignment, object detection results, and activated joints produced by the class activation map for a 5-frame clip from the NBA dataset. The results demonstrate that the reassignment strategy successfully selects athletes and referees from a multitude of detected candidates, while also detecting fast-moving basketballs. The class activation map highlights the model's focus on the shooter and referee when the shooter attempts a 2-point shot. Furthermore, the authors visualize the TSNE feature embedding on the NBA dataset for different graph structures in Figure 4. The results indicate that the proposed multi-person object graph facilitates clear separation of each class, while producing a reasonable distribution of similar classes in the embedding space. Specifically, the 2-point layup failed offensive rebound and 2-point layup failed defensive rebound samples are closely located, demonstrating the effectiveness of the proposed graph structure in capturing nuanced differences between action classes. The visualization of the embedding feature space provides insight into the learned representations, highlighting the discriminative power of the proposed approach. The comparison of keypoint-based methods on the Kinetics 400 dataset, as presented in Table 6, showcases the superior performance of the proposed method, MP-GCN, and its variants. This underscores the critical role of object keypoints in enhancing recognition accuracy. The validation of the method's generalization on the Kinetics 400 dataset further emphasizes the importance of object keypoints for recognition accuracy. Notably, a performance gap exists between skeleton-based and video-based methods, indicating potential avenues for future research. Addressing this gap could involve exploring new methodologies that leverage both types of data to achieve optimal performance. The proposed pipeline for skeleton-based group activity recognition significantly contributes to overcoming traditional human skeleton representation limitations. By utilizing advanced keypoint-based methods, such as MP-GCN, this approach can provide more accurate and robust activity recognition in complex group settings. The paper discusses the application of a panoramic graph in a skeleton-based group activity recognition (GAR) system, supported by several grants from the National Natural Science Foundation of China and other organizations. It cites various studies on activity recognition, including works on bot sort, sum product networks, Monte Carlo tree search, and hierarchical random field for collective activity recognition. The authors also reference research on convolutional relational machine for group activity recognition, open pose for real-time multi-person 2D pose estimation, and structure inference machines using recurrent neural networks for analyzing relations in group activity recognition. The paper provides a comprehensive overview of the current state-of-the-art in group activity recognition, emphasizing the importance of considering relationships between individuals within a group to accurately understand collective activities. The authors present a comprehensive overview of the methodologies employed in the study, highlighting the significance of each component in the analysis. Specifically, they detailed the application of advanced statistical models to identify patterns and trends in the data. This approach enables the researchers to draw meaningful conclusions about the relationship between variables, shedding light on previously unknown interactions. The paper also delves into the limitations of current methodologies and proposes novel techniques for future research, demonstrating a commitment to pushing the boundaries of knowledge in the field. The research paper reviews recent studies on group activity recognition, focusing on the application of skeleton-based graph attention reasoning, GAR, via panoramic graph. It discusses various approaches and techniques employed in this field, including the use of Microsoft COCO dataset, NTU-RGB plus D120, and other benchmarks for 3D human activity understanding. Liu et al.'s 2020 proposal on disentangling and unifying graph convolutions for skeleton-based action recognition is highlighted as crucial. Similarly, Pei et al.'s 2023 introduction of a guided transformer for group activity recognition, leveraging relational reasoning, is noted. The concept of sparse videotubes for joint image and video learning, proposed by Piergiovanni et al. In 2023, and the use of self-attention augmented conditional random fields for empowering relational network, suggested by Pramono et al. In 2020, are also reviewed. The paper covers the benefits of 3D pose and tracking for human action recognition, as discussed by Rajasegaran et al. In 2023, and the heat mapping of people involved in group activities, proposed by Sendo et al. In 2019. Additionally, the authors discussed two-stream adaptive graph convolutional networks for skeleton-based action recognition, introduced by Shi et al. In 2019, and the confidence energy recurrent network for group activity recognition, proposed by Xu et al. In 2017. The paper concludes with a discussion on stronger, faster, and more explainable graph convolutional baselines for skeleton-based action recognition, as suggested by Song et al. In 2020 and 2023, and the use of deep high-resolution representation learning for human pose estimation, proposed by Sun et al. In 2019. The research on group activity recognition employs various methodologies, including skeleton-based activity recognition, dynamic inference networks, and graph convolutional networks. Studies such as recurrent modeling of interaction context for collective activity recognition, and bilinear programming for human activity recognition with unknown MRF graphs, have made significant contributions. Additionally, works on social adaptive modules and hierarchical graph-based cross-inference networks highlight the diversity of approaches in this field, emphasizing the importance of understanding interactions within groups. The skeleton-based group activity recognition via spatial-temporal panoramic graph research paper on page 19 delves into the details of keypoint acquisition. It commences by elucidating the utilization of the pre-trained Yolov 8x pose model for estimating human skeletons in the volleyball weekly supervised and NBA datasets. This approach adheres to the official implementation of Yolov 83, conforming to the COCO keypoint layout. The paper then delves into pose tracking, employing the integrated BO-TSORT tracker with default YOLO tracker settings. Figure 1 is included to visualize the skeletal data used in the experiments, highlighting the skeletons extracted from the NBA dataset during instances of high-speed camera movement. This figure serves as a testament to the efficacy of the approach in capturing accurate skeletal data even under challenging conditions. The paper introduces a novel approach to skeleton-based action recognition in sports videos, focusing on the challenges of detecting and tracking key roles within a team. It highlights the importance of adopting a reassignment strategy to accurately track important individuals across frames, as the number of individuals detected can frequently exceed 20 in many frames. The authors utilize the YOLOV8X model for keypoint extraction, fine-tuning it on a custom dataset for 50 epochs. The results show that basketballs and basketball nets are detected in approximately 75% and 90% of the frames, respectively. This underscores the efficiency of the YOLOV8X model in detecting relevant objects within sports scenes. A comparison of the flops for RGB backbones used by prior works and YOLOV8X is also presented, indicating that YOLOV8X is more efficient than backbones such as VGG16 and VGG19. The task of skeleton-based action recognition only uses an off-the-shelf pose estimator, emphasizing the need for efficient backbone models. The paper's findings underscore the necessity of developing effective strategies for detecting and tracking key roles in team sports, particularly when dealing with large numbers of individuals and complex scenes. The proposed approach contributes to the advancement of action recognition in sports videos, providing insights into the challenges and opportunities presented by this research area. The distribution of detected individuals and objects in frames from the volleyball and NBA datasets is crucial for enhancing the accuracy of skeleton-based gesture recognition algorithms. Figure 2 illustrates the variability in the number of detected people in each frame, with a higher variability observed in the NBA dataset. This variability could impact the performance of gesture recognition models if not accounted for. The distribution of track IDs in each clip for both datasets is also presented, showing a higher maximum track ID per clip in the NBA dataset, indicating a greater number of unique individuals being tracked across frames. The distribution of detected basketballs and basketball nets in each frame is relatively consistent, with a slight increase in variability observed in the number of detected basketball nets. Figure 3 compares the average track length per clip for the estimated skeletons from the NBA dataset, demonstrating that the original estimation strategy results in an average track length of 22.7. Sorting by confidence slightly increases the average track length to 22.9, while the proposed reassignment strategy significantly improves the average track length to 26.6, indicating a substantial enhancement in the continuity and accuracy of the skeleton-based gesture recognition. Understanding the distribution of detected individuals and objects within frames is vital for enhancing the accuracy of skeleton-based gesture recognition algorithms. The proposed reassignment strategy can significantly improve the continuity and accuracy of these algorithms, highlighting the importance of considering the variability in the number of people and objects within each frame. The efficiency comparison of RGB and pose backbones is crucial for real-time applications, emphasizing the importance of efficient pose estimators. The reassignment strategy is introduced to mitigate issues of missed detection and lost tracks, significantly improving the average tracking length and accuracy. The performance of the proposed method using various skeleton extraction methods is showcased, highlighting a marked improvement. Additionally, the data pre-processing aspect is detailed, including the development of 4 types of input features for skeleton-based human action recognition. The authors present a comparative analysis of their method with other widely used pose estimation and tracking algorithms on the NBA dataset, focusing on multi-camera association, MCA, accuracy. Their approach, which utilizes a panoramic graph, achieves an MCA of 69.21%, outperforming existing methods such as HRNet, Alpha Pose, JDE, YOLOV 8X, and BO-TSORT. This improvement is attributed to the use of a novel feature extraction process that incorporates joint and bone motion features, as well as visibility predictions from the pose backbone. The input features are designed to capture both absolute and relative joint locations, bone vectors, and their angles relative to the coordinate axes. The authors also detailed the calculation of joint and bone motion features, which involve differences between consecutive frames and 2-hop frames. These features are then fed into separate input branches for processing. This approach demonstrates the effectiveness of incorporating motion information into the feature extraction process for improving MCA accuracy in skeleton-based global action recognition tasks. The paper presents a comprehensive analysis of various methods in skeleton-based action recognition, focusing on the volleyball and NBA datasets. It compares keypoint-based methods and graph convolutional networks, GCNs, to demonstrate the effectiveness of the proposed multi-person graph structure. Table 3 illustrates the comparison with state-of-the-art methods that leverage only keypoint information on the volleyball dataset, where our method achieves the highest accuracy of 95.5%. Table 4 compares our method with GCNs on both datasets, highlighting the improvements in recognition accuracy. The detailed comparisons emphasize the superiority of the proposed method in both keypoint-based and GCN-based approaches. The paper's findings underscore the potential of the proposed multi-person graph structure in enhancing the performance of skeleton-based action recognition. This is particularly significant as it outperforms existing state-of-the-art methods and GCNs, which are commonly used in this field. The proposed method's effectiveness in recognizing actions from keypoint information and its ability to leverage GCNs make it a promising approach for future research and action recognition. The application of a skeleton-based GAR method via a panoramic graph on various datasets, including volleyball fully supervised, volleyball weakly supervised, and NBA, demonstrates high performance on both volleyball datasets when using the same ensemble technique. However, directly transferring these methods to group activity recognition does not yield the best performance, as they are designed for single-person action recognition. Additional qualitative results are available but not included in the main paper due to page constraints. The authors visualize the feature embeddings of different graph structures on the volleyball dataset using TSNE, as shown in Figure 5. The results demonstrate that the proposed multi-person object graph facilitates a clear separation of each class, outperforming the baseline and panoramic graph structures. In the weakly supervised setting, the overall accuracy decreases due to the confusion between similar actions, such as left set and left pass, and right set and right pass. This is attributed to the absence of ground truth detection boxes, leading to missed detection and inaccurate tracking of key actors. In the NBA dataset, the most confusing cases are layup fail of flay-up fail def, which can only be differentiated by whether the offensive or defensive team gets the rebound after the ball is thrown. The authors then present additional ablation studies, including experiments on network modules and interbody graph topologies. Table 5 illustrates the impact of different input branches and modules within the basic block, demonstrating that each component substantially contributes to the model's recognition capabilities. Specifically, the study examines the effect of removing the SGC module and TCN layer, replacing the latter with a standard 5x1 temporal convolution. Table 6 shows the impact of various interbody links on the volleyball fully supervised dataset. The authors experiment with several connection strategies, including none, fully connected, linear, and pairwise connections. The results indicate that the pairwise connection strategy achieves higher accuracy and brings a more stable training process. The authors plan to explore a broader range of topological structures for interbody connections in future research to potentially enhance performance further. The authors conduct a thorough evaluation of their skeleton-based graph attention network for human action recognition, presenting a comprehensive assessment of different network modules on the volleyball and NBA datasets. Table 5 reveals that the proposed J plus B plus JM plus BM module outperforms other configurations, achieving a mean class accuracy (MCA) of 92.77% on volleyball and 75.96% on NBA. A further investigation into the impact of interbody links on MCA, as shown in Table 6, demonstrates that the pairwise interbody link approach, denoted as ARS, achieves the highest MCA of 95.54% on the volleyball dataset, surpassing fully connected and linear interbody links. This highlights the significance of carefully designing interbody links for robust human action recognition. The authors also examine the effect of input dimensionality on MCA, as presented in Table 7. The results indicate that incorporating a visibility input into both two-dimensional, x, y, and three-dimensional, x, y, v, input data improves MCA by over 1%. Notably, the three-dimensional input with visibility evaluation achieves an MCA of 75.96% on the NBA dataset, underscoring the importance of input dimensionality in human action recognition. These experiments collectively demonstrate the efficacy of the proposed network architecture and provide valuable insights for future research in this domain, emphasizing the need for careful consideration of interbody links and input dimensions to achieve robust human action recognition.